Hi, today we'll be talking about near optimal mean estimation with unknown heteroskedastic variances. I'm Spencer, and this is joint work with Greg Valiant. So what is this task of heteroskedastic mean estimation? We want to estimate some mean mu in R from samples x1 through xn. Each sample xi is some Gaussian with mean mu and possibly different variances sigma I squared. Importantly, we don't know the sigma I for each sample I. So how do we estimate the mean from data of unknown but varying quality? For some motivation, suppose we wanted to estimate some physical quantity, like temperature, and we had a bunch of sensors with unknown and varying quality. Maybe our low-quality sensors look like Gaussians with mean mu, but high variance in the bottom left-hand corner. Our high-quality sensors are low variance, but what we actually observe, since we aren't told which ones are low variance and which ones are high variance, is some mixture of these things, as we see in the bottom right-hand corner. And the real question is, how do we leverage this sort of data as well as possible? As some simpler folklore to warm us up, if all the sigma I are the same, then the empirical mean and median attain rates sigma over root n. And throughout this talk, we'll use O tilde notation to suppress multiplicative log factors in n. And if the sigma I are different, but we do know them, so we know the variance of each sample, then what we'd want to do is upweigh the low variance samples and downweigh the high variance samples. And it turns out weighing things proportional to 1 over their variance attains this rate in the bottom right-hand corner. The trickiness of this heteroskedastic mean estimation problem we study is that we don't know the variances of each point. So we can't just upweigh the good ones and downweigh the bad ones. Instead, we have to figure out some other structure to leverage in our algorithm. Maybe it helps to work through some existing estimators and how they perform in this heteroskedastic task. The most naive estimator is to just take the empirical mean. But actually, it can perform quite poorly. Say we have n-1 samples with small variance, maybe sigma I equals 1, but one sample with super large variance, right? Just to make sure the problem is clear, this one sample isn't adversarially chosen to be super negative or super positive. It's just an unbiased Gaussian, but with super large variance. Even then, now the variance of our empirical mean is ruined by this one sample. So the empirical mean performs awfully for this task. A natural follow-up then is the median good? It did work well for that last example, but it has a similar failure mode where maybe we have n to the 0.4 samples with very small variance, and the remaining samples have super large variance. Maybe you can think of it as infinite. And we still get kind of infinitely bad performance. But it's not like this instance was impossible. There is some sort of clustering. If we just look at the data, we kind of know roughly where the mean mu is because there's a cluster of samples. And since everything is this Gaussian with the real mean, then clustering is actually some sort of evidence that the mean really is somewhere. One estimator that does leverage this sort of clustering is the modal estimator, studied, for example, by Chernoff in 64. And what the modal estimator does is it estimates the point mu hat that has the most samples within W of mu hat. Some similar estimator is the that looks at maybe the k closest cluster of points and maybe takes the midpoint of the k points that are closest to each other. And prior works are mostly hybrid estimators that leverage the modal estimator, the k closest estimator, and or the median. So if we want to compare prior works, it might be a little tricky at first because closed forms are kind of weird to compare. But one nice benchmark is a subset of signals benchmark, where we say we have m low variance samples, maybe those are our signals, and what error can you promise to achieve regardless of the variance of the remaining n minus m samples? This benchmark was introduced by Liang and Yuan in 2020. And it lets us graph things quite nicely. So here the question is, given m samples with sigma I bounded by 1 of my n total samples, the remaining samples can have any variance possible. What error can I guarantee with high probability? And here what we've plot on the x-axis is m, the number of variance-bounded samples on the log scale. And on the y-axis, we have the error also on a log scale. So the first work to give this a TCS treatment is the work of Chirichetti, Dasgupta, Kumar, and Latanzi, which focuses really on the case where I have very few samples with bounded variance. But they also attain this lower bound in our picture with the dashed yellow line. Now, with the dashed blue line and the solid green line, we have the estimators that are using this sort of hybrid combination of median, k-closest, and modal estimators by Liang and Wan, Devroy, Latanzi, Lugosi, and Zivotofsky, and Pensia, Jog, and Low, kind of all interpolating along the straight line. But Liang and Yuan also give this lower bound with sort of a divot. And the question before our work was, is the optimal rate this straight line that previous approaches all get, or is it this weird rate with a divot? And what we resolve is, yes, actually, it is this weird rate with a divot, and we introduce new algorithmic ideas that get this sort of guarantee. To give some sort of instantiation to make sure this plot is readable, right? For example, with prior work, if you wanted to get little o of one error, you needed more than n to the 1/2 or root n samples. But with our work, using this purple line as the upper bound, we can get little o of one error once m is more than n to the 1/4 samples. And everything here is hiding polylogarithmic factors, of course. So the main result of our paper is getting this guarantee with the divot. So consider we have n Gaussian samples with a common mean. So xi is a Gaussian with mean mu and variance sigma I squared. And m of these variances are bounded by 1, but the variances are unknown to the algorithm, and the samples are presented in arbitrary order. Then with high probability, we can get the rate that is that with the divot in the previous picture. And moreover, our algorithm is scale invariant and translation invariant. Interestingly, there's also an extension to higher dimensions. So maybe you could consider the multi-dimension problem, where mu is this mean we're trying to estimate. It's a d-dimensional vector. We want to observe xi each with mean mu and variance sigma I squared times the identity matrix. And as d gets larger, the problem actually gets easier because we have more information about which samples are high quality. So then the natural question might be, at what value of d can we start getting guarantees as if I told you the variance of each point, sigma I? So this was studied by Chirichetti, Dasgupta, Kumar, and Latanzi in 2014. And they showed that when d is at least log n, you can get the rates roughly as if you knew the variance of each sample. They, for some motivation, study this through the lens of what if you're dealing with crowdsourced data, where each of these correspond to a user labeling some data. Each dimension is maybe some different item they're labeling. As you have higher dimension, you've seen more labels from each user, and you have more of an idea of what the variance is for that user. Roughly the way they attain this known variance rate for d greater than log n is by thinking for every pair, we can estimate the sum of their variances, sigma I squared plus sigma j squared. And the reason you can kind of do this is if you think about what does the difference between xi and xj look like in one dimension? It's a Gaussian with mean 0 and variance sigma I squared plus sigma j squared. And if I do this for d different dimensions, once d is at least log n, I can approximate the sigma I squared plus sigma j squared quite well. Interestingly, our one-dimensional main result allows us to use similar techniques to show that even d equals 2, 2 dimensions is enough. So we don't need log n dimensions to get this new variance rate. So our result says that if we have n two-dimensional Gaussians with samples all Gaussian with the same mean and variance is proportional to sigma I squared I, then again, the variances are unknown to the algorithm, arbitrary order. We have an algorithm that gets guarantees this quantity in the bottom left corner. Now, this quantity in the bottom left is almost exactly what we saw earlier in folklore for known variances, but the only difference being A, polylogarithmic factors, but also B, if you look at the summation, we're missing the I equals 1 term. So instead, the summation starts at I equals 2. And this is kind of inherent, because if I have one sample with variance 0, there's not really a way of telling that. But for example, if I had two samples of variance 0, I would immediately have exactly the mean because I would see two samples that are exactly the same, and I would know that would mean that has to be the mean. But for the rest of the talk, we'll be talking about our main result, heteroskedastic mean estimation in one dimension, kind of actually the harder problem. To do this, let's revisit the modal estimator we talked about earlier. So suppose we're in this quite simple case where we have n samples, each from a Gaussian with mean 0 and variance 1. And we want to analyze how does the modal estimator perform with a width parameter w equal 1. So again, the modal estimator would be choosing the mu hat that has the most samples within one of it. We'll use this notation to count the number of samples in some range. And kind of as a spoiler, the mean and median, as we know, would get error proportion with sigma over root n. But the modal estimator will get worse error of sigma over n to the 1/3, so polynomially worse. And it's good to study why does this happen, and to do where does this n to the 1/3 come from, and to do so, we'll say in the simple setting, how close should the modal estimator get to the correct mean of 0? And to make our calculations easier, maybe we'll roughly study when does centering the modal estimator at 0 have strongly more samples within one of it than centering it at delta. So that's the question we're trying to ask. And maybe to compute this, we could say, what is the expected difference in standard deviation of the difference of these quantities and see when delta is large enough to overpower it. So if we calculate the expected difference, I'm skipping some route calculations here. The value is n times delta squared. And again, I'm skipping some calculation, but the standard deviation is root n times delta. So when does the expected difference overpower the standard deviation? This is just when delta is much greater than n to the negative 1/3. And this is where the error of sigma over n to the 1/3 roughly comes from. But actually, we make this crucial observation that when the modal estimator is performing this poorly, when the error is on the order of n to the negative 1/3, we could actually see it. So for example, if mu hat was overestimating by n to the negative 1/3, then what we might observe is that the left half, the number of samples within 1 to the left of mu hat, is significantly larger than the number of samples within 1 to the right of mu hat. So to get some intuition for that, say we center at n to the negative 1/3. That could be a value that the modal estimator is overestimating at. How many more samples are nearby within 1 to the left than within 1 to the right? Well, if we calculate the expected difference, this is going to be n to the 2/3. And if we calculate the standard deviation, this is root n. So it's noticeably imbalanced. The expected difference is overpowering the standard deviation. And this kind of gives you some fix for the classical setting where all the variances are equal. We can fix the modal estimator by ignoring all mu hat that are noticeably imbalanced, and then just taking the modal estimator, the one with the most samples within W of it, of the balanced mu hats. But this doesn't necessarily tell us how to solve the more general heteroskedastic problem. And it's not even clear how do we choose W, our width parameter, in this more general case and in a scale invariant way. So to do so, let's examine this phenomena of balance. If it's not clear yet, it kind of seems like balance is important. And maybe what we should consider is what happens when we look for estimates mu hat, where the number of samples within width W to the left and right are approximately balanced. What does that phenomena imply? And roughly, maybe what it implies is that either your estimate mu hat is really good, like on the left-hand side, or it's really bad and kind of in this flat tail part of the density. So then we could kind of think a little further and say that if balance is more delicate, then our estimate is probably good. So say we shift our balance, we perturbed it by delta. What happens to our balance if we perturb our estimate by delta? Well, if we were in the flat part of the tail, then moving our estimate delta to the left and delta to the right remains with our sides being roughly balanced. But if we had mu hat being the correct estimate, then moving delta to the left should have the right half becoming much heavier, have way more samples. And similarly, moving delta to the right will have the left half become much heavier. And this is the crucial phenomena of which our paper is based on. We prove that if we see this sort of delicate balance, where you move to the left and the right half becomes heavy, and you move to the right, the left half becomes heavy, then we can conclude with high probability that the mean is within delta of mu hat. meaning we kind of have this sort of confidence interval that mu is inside mu hat minus delta to mu hat plus delta. The crux of the analysis and a lot of the difficulty of this paper comes from proving that there exists a combination of mu hat, delta, and w that helps you find the mean near optimally. So maybe delta is small enough so that the confidence interval that you attain is a small confidence interval of the correct width to be solving this problem at the optimal error guarantee. So this kind of gives you some idea of an algorithm immediately. We'll try all values of this tuple mu hat, delta, and w, and intersect all the confidence intervals we obtain. Wrapping up, the main intuitions we've had so far is that we fixed the modal estimator. This let us push our intuition to design a balance finding algorithm that nearly optimally resolves the subset of signals benchmark. And while the algorithm I just suggested, trying all tuples, maybe sounds like it takes infinite time, we can speed it up to be near linear time by choosing carefully chosen tuples. And the same techniques that let us get our main result of this one-dimensional heteroskedastic mean estimation also lets us get the known variance guarantees even for two-dimensional Gaussians, not needing log n dimensions. Thank you.